On the other hand, if I do the following, that artificially I make this sequence repetitive, periodic, then I don't have a problem, because when I go on moving it, something or other will come because of periodicity. So, if you use that kind of periodic sequence, which is artificially made periodic, and then find out the correlation, this is called the periodic correlation. In periodic correlation, you don't have to artificially put zeros. Some values exist because you made this sequence periodic. So, both kind of correlations are defined, linear correlation as well as the periodic correlation. That is, if this signal exists only for one duration of n samples, then you have to have a linear correlation by putting zeros. But if by chance your input signal itself is periodic, so it goes on coming in a periodic manner. So, in correlation there is no issue, because they will always be able to correlate with respect to a defined value for the x2 n minus k. So, these two correlations are distinguished between have to be very clearly understood, linear correlation versus the, and the property of the correlated function at the end of this operation will be different for linear and the so called periodic or cyclic correlation. So, depending upon your problem, the kind of waveform you are getting, whether repetitive waveform you are getting or only a periodic waveform you are getting, you have to end up into linear correlation or a cyclic correlation. In radar systems or any communication system, because this signal is always repeated in terms of carrier modulation or say code or whatever it is, so you will always end up into the idea of cyclic correlation. You never send one pulse and keep quiet. You modulate the pulse for every period. So, it is a repetitive waveform. So, the cyclic correlation is the most commonly used. So, you have a difference between the linear correlation and cyclic correlation or periodic correlation. If you want to do the Fourier transform of this with linear correlation in mind, then what you need to do to get the Fourier transform would be to extend the signal to 2n minus 1 length by putting artificially zeros, and similarly this also 2n minus 1 by putting artificially zeros, so that there is a match between these two. And the signal now, the correlated signal will be length equal to 2n minus 1. So, when you take the Fourier transform of the 2n minus 1 number with zeros in it and the 2n minus 1 with zeros in it for the second one, and then multiply these two Fourier transform, you get the Fourier transform of the correlated signal with length equal to 2n minus 1. Okay. That is the Fourier transform of the linear correlation. But periodic correlation, because the signal is periodic, you can take n signal, take the that n signal, take the Fourier transform, multiply these two Fourier transform, that give you Fourier transform of the correlated signal. So, depending upon which correlation you are talking about, the Fourier transform of the correlated signal will be different, because the correlated signal is different. So, Fourier transform will also be different. Okay. In any case, whether you do it by linear correlation or the periodic correlation, so to do a correlation operation, what you need to do is take one sequence of some length, another sequence of length, and then go on sliding this sequence for different values of n, and see what is the product between these two, and then sum up for every value of n. Are you with me? Okay, good. This is a more time consuming operation in a computer. So, what people suggested is that instead of doing it in time domain, you go to Fourier domain and do the FFT on them and multiply the FFTs appropriately as a linear, depending upon linear or cyclic, and then take inverse Fourier transform. So, how many Fourier transforms are doing? 3 times, right? One on x1, one on x2, one on the multiplied value. So, the 3 Fourier transforms are doing. Even then, how much will be the computations you do? 3n log n compared to the Fourier transform on the original one is much product and then Fourier transform and product. So, the time that is consumed in doing it the roundabout method of x1n to x1m appropriately linear or cyclic, and similarly x2n linear or cyclic, multiply these two and get x of n and corresponding get x of n, and then invert it. So, the number of computations, if you go by this route, turns out to be still much less than the amount of time that you require to do a direct correlation. So, people have adopted this method of finding the correlation between two functions, apparently going roundabout, but still turns out to be faster because of the reason that FFT gives you a lot of computational advantage. This method of doing correlation is what is known as the fast correlation in literature. In the fast correlation, you do FFTs on both and then multiply and then take the inverse FFT. So, anybody now who does a correlation operation doesn't do this going on sliding business, and instead of that you take the Fourier transform, multiply, take inverse transform. Okay, this is the what the literature is called as a fast correlation, and these are all byproducts of this so called FFT. So, you go back and look at this from your 102 notes, first for your Fourier transform algorithm, and then try to find out the actual processing. So, this here have been this indexes here 0 1 written out in terms of a binary number, and you read the binary number from backwards and then rearrange these numbers in that sequence. Remember that or not? If you have 4 samples 0, 1, 2, 3, then this is binary number is 0, 0, 0, 1, 1, 0 and 1, 1, right. So, this is my x0 sequence x0, x1, x2, x3 and minus 1 n samples. Then you read this backwards, this is 0, 0, so it becomes x0 first, and if you read backward this becomes 1, 0, so this becomes x2, right. Read backwards, this becomes equal to 0, 1, this becomes x1, I read backwards, it becomes 1, 1, it becomes x3. So, now you shuffle these columns, x1, x2 and x3, you shuffle them into this sequence x0, x2, x1 and x3, and then rearrange the corresponding terms here, then this broken down into matrices like this, and this matrix is now the size n by 2, and this operation again can be done exactly like what you did for n, and go on going down. Finally, 2 to the power of n, so it can come down to size 2, which gives a simple butterfly, which is equal to AB, and this is A plus B, and this is A minus B pictorially. So, the whole operation can be represented in terms of this butterfly.